Let's find the Taylor polynomial of degree 2, the quadratic approximation, for the function of equal to the square root of 2x plus 3y, and I've chosen the point 3, 1, which means I want a to be 3 and I want b to be 1 when I'm done, but we'll worry about that. Remember, we have to take the function, we've got derivatives to take, so I'm just going to try to find all the derivatives first and then plug in the points, and finally, once we have all the points, maybe we can just write down the answer. Now, the original function should just be f, and the formula for that is just 2x plus 3y to the 1/2. Not bad. We need the partial derivative with respect to x, so we're going to do that. I need to say I've got blob to the 1/2, so it's 1/2 times blob to the minus 1/2 times the derivative of the blob, the inside with respect to x, so that's just going to be 2, like that. I also need fy, like that. So I'm going back to my original function. I've got blob to the 1/2, but now we're taking the derivative with respect to y. So that's going to be 1/2 times 2x plus 3y to the minus 1/2 times 3, like that. I need fxx. One thing I do want to notice at the moment is those 2's cancel. So when I take the derivative, I don't have to worry about those. So I just want to take the derivative of blob to the minus 1/2. So that's going to be minus 1/2 times the blob, 2x plus 3y. This is going to be the minus 3/2. Minus 3/2 times the derivative of what's inside, which is just going to be 2. Now, we can take fxy or fyx. We're going to get the same answer this time. So I'm just going to say, let's just do fxy. If I want to take fxy, I'm going to look at fx and take the derivative of that with respect to y. So I still have blob to the minus 1/2. So I'm going to bring down the minus 1/2. This is going to be the inside, which is 2x plus 3y. There should be minus 3/2. And now times the derivative of what's inside with respect to y. Well, there's a 3. Now I don't have to take fyx because it's going to be equal to fxy. I do need fyy though. So fyy, I need to look at my formula for fy. I'm going to pull out the 3/2 before I take the derivative, and now I'm going to take the derivative, so it's going to be minus 1/2 times 2x plus 3y to the minus 3/2 times 3, and that's the only one I think where I actually have to do some simplifying. That's going to equal to minus 9/4 times 2x plus 3y to the minus 3/2. And now I want to plug in x equals 3 and y equals 1. Well, if I do that here, I get 9 to the 1/2. I guess we can just write it like that. 9 to the 1/2. Well, that is just 3. That's a nice number. When I plug in x equals 3 and y equals 1, what I'm going to get is 9 to the minus 1/2. And that's just a third. When I plug in x equals 3 and y equals 1, what I'm going to get is 1/2 times 1/3 times 3. Those 3's cancel and just get 1/2 here. That works out well. When I take fxx and I want to plug in, I'm going to notice that those 2's cancel. So all I'm going to get is equal to minus, let's see here, I'm going to have 9 to the minus 3/2, which is actually just minus 1/27, like that. When I plug in 3, 1 here, this is going to be minus 1/2 times 9 to the minus 3/2 times 3. So that's going to be, let's see here, I'm going to get minus 1/2. 9 to the minus 3/2 is 27, like that, times 3. One of the 3's cancel. Yes, so I'm left with a 9 down here, and that 3 is gone. And so I get minus 1/18. This is minus 1/18. And now I think maybe the only messy one, when I plug in x equals 3 and y equals 1, I'm going to get minus 9/4 times 1/27th, and a 9 cancels and a 3 is left. And so what I'm left with here is equal to, minus 1/12. Now, I think we have everything we need to now write down the quadratic approximation. I do want to remember what everything is, right? This is fx, this is fy, this is fxx, this is fxy like that, and this is yy. I'm only doing that because I have to erase what's here to be able to write it down. I think we can write it down without too much sweat, but let's just do it. And here we go. I'm just going to write down q of xy. I'm going to talk my way through it. I'm always supposed to, well, this actually starts out like the tangent plane, right? So it should start out f of ab, which is 3. The next thing in the tangent plane is fx at ab, and so there's 1/3, and I should have my x minus 3. The tangent plane also has fy times y minus b, and so that's just going to be 1/2 times y minus b. So just like in Calc 2, the quadratic approximation starts out just like the linear approximation, but now there's more. What we're supposed to have is 1/2, just like it had in Calc 2. I want fxx, so that's going to be minus 1/27th, and then x minus a, quantity squared. Now I should have 1/2 fxy plus 1/2 fyx, but they're going to wind up being the same here. So we're just going to have 1 times fxy, which is minus 1/18th. And this is going to have both involved, x minus 3, y minus 1 like that. And then finally, I want fyy, which is, well, I need my 1/2 times fyy minus 1/12. This is fyy, so what I'm going to get here is y minus 1, quantity squared. And we have our quadratic approximation. I'm not going to actually use it, but I will say, hey, what would it be used for? Yes, we could use this to estimate the function value of any point that's close to 3,1. For example, if I wanted to say, let's estimate f of 2.9, 1.05. Our choices are either to plug that thing into the square root, which is hideous, or in our quadratic approximation, anywhere I see a 2.9, anywhere I see an x, put a 2.9, anywhere I see a b, put a 1.05, and you're going to find out, for example, that you're going to get 3 plus a lot of tiny numbers. So the estimate actually is not hard to get. It's much easier than using square root, but we had to take a lot of derivatives to get here. And that's how you would find a Taylor approximation, and this is the kind of problem that they would ask us to use it on.